In Unit 2.1, we'll review average rate of change over an interval. And then what we'll learn to do is we'll learn how to find the instantaneous rate of change at a single point. So you're not going to be using 2 points. There will not be an interval, just a single point. And we're going to develop a formula for that, first by approximating the instantaneous rate of change, just using a super tiny interval. And then we're going to add some precision to that to get the exact instantaneous rate of change at a single point. And finally, we're going to explore some different notations that they have for instantaneous rate of change that can be a little confusing. So that's where you probably want to keep some good notes. So a picture's worth 1,000 words, and so is a good word problem. So here we go. My border collie, Shannon, is obsessed with catching balls, frisbees, sticks. You throw it, she runs after it. She practically flies through the air. And because I am a math nerd and proud of it, I've graphed one of her recent flights. So I ask you, how would I find her average rate of change in feet per second between the first and fourth second? Well, I'd use 2 points. And so let's pick 1 second for feet and 4 seconds, 10 feet. And then you probably recall from Algebra 1 that what we're going to do is we're going to find the slope of the line that connects those 2 points. That's called the secant line. And you recall that slope is a change in y over the change in x. So let's go ahead and do this. So we've got 10 minus 4 over 4 minus 1. That becomes 6 over 3, which is 2. And since this is a rate, we have to use our units. So 2 feet per second. P.S. On the AP exam, they take off points if you don't include units. So don't lose points unnecessarily. Try a couple of examples as you might see them on the AP exam. In the first one, you're given a table of values and your x interval is going between 2 and 30. So the change in y, so it's going to be f of 30, that's a y value, minus f of 2, all over 30 minus 2. And then you find your corresponding y values and plug them in. So this is going to be 7 and negative 2. 7 minus negative 2 is positive 9. 30 minus 2 is 28. We don't have units in this case, but thank you for remembering that. The second one is generally you see it in what we call MCQs, multiple choice questions. And so we're being asked to set up an equation. Okay, well, I know that an equation has an equal sign that shows the average rate of change of f on this interval. So that's going to be f of b minus f of 0 all over b minus 0 is, so that's where your equal sign is going, 0.05. If you need to pause and think about that for a minute, go ahead and then come back, and we're going to plug in the function f of x. So the first f of b would be 2 sine b plus cosine b, and f of 0 would be 2 sine of 0 plus cosine of 0. My denominator is just going to become plain old b. That's equal to 0.05. And if you don't have your trig down, now's the time to get it. Sine of 0 is 0. Cosine of 0 is 1. So this just becomes 2 sine b plus cosine b minus 1 all over b equals 0.05. Okay, so let's set up average rate of change equations showing how we would find the slope of the secant lines for both of these graphs. That would be the average rate of change. So for the top one, it would be change in y, so f of x plus h minus f of x all over a plus h minus a, and we can cancel out the a's if you want to. In the second one, my y's are f of x minus f of a all over x minus a. So I'm just using my whole change in y over change in x. Hang on to that thought. Make sure you understand it, because we're going to go into greater depth in just a moment. Next, what we're going to do is we're going to explore instantaneous rate of change, and we're going to look first at an approximation of instantaneous rate of change. Now, when I'm asking you to find instantaneous rate of change, I'm asking you to find rate of change at a specific point. So for instance, if I said, hey, yeah, I understand what the average rate of change is for this dog from 1 to 4 seconds, but she's not always going the same speed. Sometimes she's going slower, sometimes faster. So when the clock has ticked 1 second off, how fast is she changing? Okay, so, well, I don't have 2 points here. And right now, rate of change, I only know how to figure out with 2 points. So tell you what, the secant line that I have right here looks similar to my tangent line. They don't have quite the same slope, but they have approximately the same slope. They're both positive. But could we make this slope any better? Well, what if we moved that second point a little closer? Like, let's say we moved it to there. So now this lime green line that's in here, I'll do it in yellow, that's green. Okay, that green line, now it's getting closer to the slope of that tangent line than what that secant line was. So the second one, there was my secant line, there was my second one. If I use a third one right there, yeah, I'm getting really, really close. And what you should start to notice is that the closer I move my x values towards 1, the better my approximations become. So in our last slide, what we're going to do for this approximation is we're going to choose some x value that's super duper close to 1 and see what happens. And we're going to say that this distance between 1 and this next point is h. So if I do that, this is my h distance. So this point right here becomes 1 plus h, and its corresponding y value becomes f of 1 plus h. So let's put that into our slope formula now using those 2 points. So we'd have f of 1 plus h minus f of 1 all over 1 plus h minus 1. And let's say I said, okay, let's move it closer and closer. Let's get it so that its width is so infinitesimal you can barely even measure it. It's going almost to 1. Well, what should pop into your head are limits. If you slap a limit notation right in front of that slope equation, then what you have is you have the precise formula for instantaneous rate of change at a single point. There we have it. Okay, let's work with some notation. So remember before, when we were just finding average rate of change, we used the slopes of the 2 points, so change in y over change in x, f of x plus h minus f of x, all over x plus h minus x, which simplified to just become h. And now since we want instantaneous rate of change at that single point, we're going to slap a limit as h goes to 0 in front of it. Okay, in the second example, our average rate of change, again, was changes in the y's over changes in the x. And then we put a limit in front of that. But in this case, we don't have an h in this. What we're doing is we're trying to move this x value closer and closer to a so that my y values get closer and closer to f of a. So I'm really moving x closer and closer to a. X is approaching a. So dog-ear this page, our average rate of change is just the slope, and we have 2 different forms here. And it's a slope of the secant line We're using 2 points, so we're going to say it's over an interval. And the instantaneous rate of change are these two equations where we just took the average rate of change and slapped a limit expression in front of it. And the instantaneous rate of change is the slope of the tangent line to the graph at one single point, not an interval. So now we're going to practice writing instantaneous rate of change expressions. So Estella's flying her helicopter, put in there it should be at some height according to this equation for the first 20 seconds. So you've got this equation for E of t, which gives us height, and there's our interval of time. And I want to write an expression involving a limit for the instantaneous rate of change of the height of Estella's helicopter at time t equals 7. So this is going to be what goes in my A position, okay, because that's the specific point. So the first form, let's remind ourselves what that is, and there you have it. And now we're just going to plug the 7 in for the A, so we have the limit as h goes to 0 of f of 7 plus h minus f of 7 all over h. And that's my first one. Remember, our second form is just this. And again, you just plug in 7 where the a is. So this is going to be the limit as x goes to 7 of f of x minus f, that should have been an a, sorry, minus f of 7 all over x minus 7. Now, spoiler alert, this is the form that we use, you'll see more frequently. However, on the AP, they tend to love these questions with the second, more obscure form. So you're going to be having to live with it, and especially come May, you're going to need to know it. So let's just get it down now. Let's practice deciphering instantaneous rate of change expressions. So let's say you're given one, and they're asking you to figure out what the function is. We recognize the form that it's that whole f of x plus h minus f of x all over h limit thing. And we recognize it's that one. The biggest clue is going to be you've got that h going to 0. So it's saying, tell me, oh, we were using a, my bad. Okay, so first tell me what the function is. Actually, it might be easier to figure out what a is. Right here, a is going to be the part that has the plus h in it. So it's going to be whatever number has a plus h. So a in this case is 4, okay? And then you take, for the function, you just cross out the a plus h part and replace it with an x. So I'm going to cross that out, replace it with an x, and then there is what f of x is. So it's going to be 5 ln of 2 over x. And you can check it, because if the second part of this is supposed to be f of a, well, if I took this 4 and plugged it in right there for the x, I'd get 5 ln 1/2. So I'm happy I got it right. Okay, let's use that same idea again. Now, x is going to be what my a value is, and my a is going to be the guy with the plus h. So what do you think a is? You can pause, turn it on. So there's the 3, because here's where your a plus h is coming in. So a is 3. And now to find f of x, I'm just going to take the first function, which is that. I'm going to cross out the a plus h part, replace it with x. So my function is e to the 6x plus 1. Now we're going to decipher using that second instantaneous rate of change formula. And we recognize it because we have x going to some number. That number is a. So that's what goes right here. X is going to 7. F of x is just going to be your first function. This form's a little easier. So it's 1 over square root of x squared minus 2x. You do the second two. Put the video on pause. Come back and check your work. Okay, so in problem number 2, first guy is your function, and there's your a. Number 3, first guy is your function, and there's your a. And that's all there is to it. It may seem a little confusing right now, but once you do your homework and get some more practice problems, I'm sure you'll be a pro.